particle tracking to study mixing in consumer products application. And speaking on the subject will be Dr. Timothy Laska. Dr. Laska is a technology leader in the beauty division of Procter & Gamble company. He began his career 20 years ago developing products and processes for deodorants category. In 1999, he started the modeling and simulation effort in the beauty division. He created several automated workflows such as the virtual racetrack and virtual mix tank that replaced slow and expensive physical testing with fast, inexpensive, and accurate simulations. He has been a heavy user of AcuSolve since 2002. Dr. Laska received his Bachelor of Chemical Engineering from the University of Minnesota in 1986 and his doctorate in Chemical Engineering from University of Wisconsin in 1991. Please welcome Dr. Laska.
Good morning. I want to thank Altair and especially Steve Cosgrove for inviting me to speak on some of the work that we've been doing on the high fidelity particle tracing. I work for Procter & Gamble. Just briefly on the agenda, I want to discuss the business profile and also our relationship with Acusim, then why we want to do particle tracing, then I want to spend most of the time looking at the application examples. Procter & Gamble is a big company. We do about 80 billion in sales. The beauty division where I work, we do 24 billion in sales. There's about 20,000 different little labels that we'll put on products, so we have a very vast product line. We have some large projects that we work on, and then most of our projects are very small. One of the things that separates us from most of the other business units is that our products are very, very thick and non-Newtonian. At rest, these fluids can be over 1 million centipoise, and they'll thin down with a shear thinning index of below 0.1 sometimes. These teams have very short attention spans, and so we need to turn the simulations around in about a 48-hour time period for them, for us to be able to influence a decision. Our relationship with Acusim has gone back to 2002. We started to use AcuSolve as part of the Orca package, which is now defunct. It's our preferred solver to study non-Newtonian mixing, and my collaborator in my business unit, we run about 3,000 mixing simulations per year. Over time, we've cooperated on many enhancements, and we've also helped fund the development of the transient particle tracer that we'll talk about later. So why do we believe in AcuSolve? Well, it makes us look good. And this is one of the first simulations that we conducted with AcuSolve. What you see is our typical nightmare where we have a very thick fluid that it's in a baffled tank, but you can see that there's pronounced stagnant zones in this region here. These dots aren't moving. You can also see that the simulation, which is a mirror image on the right, has very similar features to the actual experiment. If you look at the unbaffled, we're able to predict what the solution was. You can see that these dye particles are immediately whipped into the batch, and it's consistent with what we observed in the simulation. And I'll let this recycle one more time just to show you one other feature to kind of illustrate the viscosity difference that we have. but you'll see some stiff peaks around the shaft, which, this fluid was one of those fluids that was about 2 million centipoids at rest, and around the impellers, the viscosity is around 10 centipoids. So this was our reason to believe that AcuSolve was good. We had a reason, and actually what I'll also point out is another solver said that this baffled was an actual optimal design, and we knew that that was not true based on the experiment. From that, we now had a reason to, this is what we call our tree of evolution, but it was a good pairing of technology and business needs. We had a real business problem that we could solve with this code. We put a lot of work in developing this virtual mix system, which is an automated workflow that takes CAD, automates the meshing and solving and post-processing. But once we've developed that technology, we started to branch off into other areas very quickly. So once we had a good foundation and trunk, we were able to rapidly develop, and we use AcuSolve for a lot more than just the particle tracing that we're going to do, or that I'm going to discuss later. But we were able to look at tank homogeneity. We're able to look at diffusion through a hair bundle of moisture. We're able to look at product cooling, able to look at the pressure that it takes to shove product through a cap, look at SMXs, look at filler designs, look at sloshing on a packing line. And really what I'm going to focus on for the rest of this talk is this particle tracing that we use to great effect to study mixing phenomena. Why particle tracing? It's non-diffusive, and one of the things that this allows us to do is to not have to blow up our mesh size to get highly resolved images and movies. You pay a big price with a volume base mesh. If you want to get double the resolution, it typically takes about 16 times longer to run the simulation, and you'll see with this Lagrangian particle tracking that we actually get much better resolution than you could get by mesh alone. The other thing is very fast, it's accurate, it's intuitive. The results that we get with particle tracing are the things that we have to explain the least. The project teams tend to get it. And it's about the only method we have to get time-weighted statistics on what environments the fluids are seen as they pass through a device. The examples, I want to talk about AcuTrace Classic, which was the original particle tracking code that we used. We used it to great effect, but it did have some limitations. And then we'll talk about some examples using AcuTrace 2, which is the transient particle tracer, and some of the advanced features. The first example is a static mixer. This is in a filler. One of the things that we have at Procter & Gamble in our division, we have probably about 200 different filling operations. The project team, this is a new design of a filler where they were going to combine two different feeds, and the question was, is the orientation of the static mixer, which occur ubiquitously throughout manufacturing plants, is it important? And what we can see is that when these two streams meet, because the blades of the first mixer are parallel to the interface of the stream, that the first set of elements, all it does is provide pressure drop and no mixing capability. Here's another example of a static mixer where it's a center-mounted injection, and I'm not sure you can see that very well, but there's a little J injector, and it goes into these static mixer elements, and you can see very highly refined detail of the striations of the fluids. And if we were to do this with scalar transport, which Steve alluded to, the thing would be all smushed out after that first element, and we wouldn't be able to see anything. You can also see that this is an example that Seltzer, who makes the SMX static mixer, what they did here is they injected with epoxy two dyed epoxies through this device, and then actually cut this device up, sliced it, and created images which are very similar. And we also are interested in mixed tanks, and here's an example of a helical impeller with a draft tube. One of the things we can do with these particles is we can accumulate how much strain they're seeing during their trajectories through the device. You might not be able to see it very well here, but there's an artifact of this simulation where there's kind of an orbiting thing up at the top. And this is one of the difficulties that we had using this technique, in that we had trouble eliminating artifacts when we had rotating devices. When we had multiple reference frames, particles, there was no clean way to resolve the visualization. So that's what we could do with the classic AcuTrace, but it did have the limitations. It was limited to steady flows. We had limited output capability. We could only look at flow variables such as temperature, velocity, species concentration, and then the stretch. It also had very limited seeding options. We could only seed at time zero the particles, and you actually had to run through a lot of hurdles to get the post-processing so that you could make a mixed tank visualization. So we embarked on this particle tracing endeavor with Acusim. We've been doing that for maybe about 4 years. And this shows I'm going to start it over. Let me just, it shows continuous emission through this inlet. It shows actually another artifact here. We're getting a wagon wheel effect because the impeller in this case was moving too fast that it looks like it's spinning backwards. It's actually spinning the other direction, but we do have smooth transitions when it goes into the impeller region. Here's another example of the same simulation, and what we can see is a stagnant region at the top of the tank where particles do not get into the top of the tank. So about 1/3 of the volume is not usable. And the reason we want to use these tanks, and I'll just, hopefully you can see this too, is the validation run where we also see the top third. We weren't able to get dye into the top third. What we use these tanks for is to buffer out upsets in an LPD process, late product differentiation, where we try to combine things through a static mixer, but if there's an upset in one of the pumps, you'll get variation in your product formulation levels, and you'll not meet your QA requirements. So you have to kind of find out what the volume required and that you need to get these tanks to filter out the variations you expect. So we can do that too with AcuSolve or AcuTrace by putting a little plane at the outlet and recording the times that the particles reside in there. And one of the things we'll note is we ran the simulation out to 3 days. So that's 257,000 seconds. So we can track this out for a long time, which you do need to get the asymptotic value. And we can see that the simulation shows it responds a lot faster than what the ideal case is, and that tells us that we need much larger tank to design much larger volume to buffer out what we want to the disturbances. Now here's something that was somewhat interesting we did recently. What they're doing here is they have a product that's on a bottom sheet that flows towards this set of rollers, and a top sheet flows down and combines, and they form a little pouch type product. The problem with this product is that if there was any oxygen in the pouch, it was unstable and would decompose. And so the mechanical engineers developed what they thought was a solution. They enclosed it in a little Lexan box. They got 3 nitrogen purge knives where they blew nitrogen at fairly high velocity. And the idea was that this knife would sweep the bottom sheet, this knife would sweep the top sheet, and there's also a knife on the backside that would sweep the backside of the sheet too. And so that's how it's supposed to work in principle. Because when I initially looked at this model, I said this looks pretty complex, so I started off with a 2D. And this is what we're able to do with particle tracking. And we probably will have to play this a couple of times, but because each time you look at it, you see new features. The main flaw in this is this knife, let me start it over. This knife here doesn't get anywhere near that top sheet. It just, because what happens is when this film and this wheel converge, it actually creates a jet and everything flows in this direction. So let's just look at that one more time. So it doesn't get there's no flow that goes anywhere near that outlet. So it basically does nothing. The other things that you'll see are pronounced stagnant regions, and that's, if you're doing mixing problems, you want to reduce the volumes of these stagnant regions. They actually form a little conveyor system themselves. This particular simulation only took really about an hour and a half to conduct, but we could see that there were a lot of flaws with the initial design. But because it was so easy to do as a 2D problem, we said, well, let's try a 3D problem. And here what we did is we colored each outlet of or inlet of each of the knives with a different color particle. So it's kind of like what you might be able to do if you had, if you could get it with colored smoke. And this is actually probably too busy to really get any idea of what's going on, but you do see certain things that occur where you get, because now we're looking at it in 3D, you have flow paths that can spill around the top sheet, which weren't available to it in a 2D problem. But to simplify it, we can look at just a small cut in the to try to mimic the 2D simulation, and we see some similar effects, but we also see that this flow is a lot less stable than it was before due to the 3D. The flow isn't as constrained, so it can move in and out of the plane and is not as stable as it was in the 2D simulation. But we still see very similar effects. This knife, there's essentially no green particles. No green particles go towards that they're desired to go out that outlet, and none do. So we've made improvements since this design, but it's always good to look at some of the failures. This device is a rotor stator mill, and due to confidentiality reasons, I can only give you one view of it. But these are used a lot in our whoops, let me get back. These are used a lot in the beauty area where we're trying to emulsify a product with oil and water. There's a rotor in here that spins at about 3,000 RPM. And what we're interested in is using some of the advanced features of AcuTrace to track what environments these particles see as they go through the device and what's the distribution. So in this case, we're just looking at the elongational strain, the diagonal components of the strain rate. We're accumulating those, and because there are some theories that the elongational components are what drive the droplet breakup. And so as we go from different scales, we can compare these distributions. And the last advanced feature that I want to discuss is, which is very new, is the bidirectional coupling. So in this particular simulation, we're taking hot particles and assigning a mass and a heat capacity and a conductivity to them, and allowing them to actually exchange the energy with the fluid. It's still under development, but it's promising, and it can be. There's some things that we need to stabilize this code in terms of conditioning, because it will get. We have achieved temperatures of 10 to the 30th, which is too high, but so in conclusion, it works as advertised. It's a non-diffusive technique. We can get very highly resolved images. It's fast, accurate, intuitive. We're able to get quantitative statistics, and the future of bidirectional coupling looks promising. The next step is to stabilize the temperature code, add species, then we'll start adding mass to the particles. So I want to thank you and have a nice day.
Thank you, Dr. Laska. So just a moment, may I request Mr. Steve Cosgrove to hand over a small memento, please. Thank you, Dr. Laska. Thank you, Mr. Cosgrove.